Okay, welcome back again. We are talking today about another kind of a second form of the chain rule that we just learned about. This one's going to be called implicit differentiation. Now, this is kind of the summary of the chapter, as in if you can kind of get this, you got it for the most part of the chapter, you understand it. It's kind of putting everything together here. Essentially what it's going to be is you're going to be doing the chain rule, but we're going to now be taking the derivatives of things that are no longer functions. And that's the difference here of what's going on. Not going to be functions. So I'll talk about what I mean on this one, and I'll do lots of examples today. So we get an equation like this. This is a normal one where it's standard function, okay? So if we take the derivative of this, we know how to do that. We know how to take the derivative. You get something like a negative 6x. Then I'm going to show you an equation like this where you now have a function that has multiple variables. You're going to have x's and y's, and the main key that I want you to get out of this is you're going to not always get y by itself. You're going to start to see other things with y, powers of y, multiple y's, and it's not just going to be a simple y equals something. So in this equation you see on the top of the screen, you can obviously rewrite it so that it looks like a function like it is down here. You can do this derivative. So nothing special there, but they're going to talk about dependent, independent variables. I'm not going to get too wrapped up in that. I just want to show you exactly what we need to do here. Okay, but what's going to happen here is we have this explicit relationship, okay, in this equation. This is what we're used to, okay, where it's just simply y equals something. Implicit is the first one where it's not exactly the y by itself. And that's the kind of stuff we're going to be taking the derivatives of today. All right, so I'm going to jump forward to this one right here. We're going to do the implicit differentiation of this equation right here. So let me go back. This is the easy one, the normal one. The derivative is negative 6x squared. We got that. Now we're going to do this one here. And you're going to see how the process is. Even though you have another letter like a y, we're going to treat this all as 4 different terms, including the 0, all these different terms, and we're just going to go find these derivatives. Now, the stuff that we're used to is, sorry, lost my screen for a second here. That. We know how to find those derivatives. Okay, so the key, though, is we are going to find d dx of this whole thing. Now, they're going to say use implicit differentiation. But I want to focus on right here for a couple minutes here is this d dx notation. We've used that before. Remember, this means take the derivative. But more than that, it means also with respect to x. Okay, so that's where everything is focused on. You're going to do everything in terms of x, with respect to x. Okay, so they're going to show you a couple of things in there. I'm just going to go right to this problem and show you how we're going to do this. Now, this answer, when I do the derivative, I'm going to come way down to the bottom here. This is like it normally is. It's a 6x. This is like it normally is. It's a 0. This is like it normally is. That's a 0. All the normal terms you've had, different powers of x or constants, those are the same derivatives you've always had. The difference is now on this weird one right here, not weird one, it's just a y, but it's something different. We're going to take the derivative of that, and it's simply going to be, well, let me go ahead. Sorry, not a 1, not a y. It's going to be 1. Okay, so we do that derivative like we're used to. But here's the deal. Anytime you take a derivative of something other than an x, you have to add on the little prime piece right here. This is the chain rule I'm talking about. Because this is not an x, which it obviously is not, it's not an x, you still do the derivative like you normally would, except when you get this y, you put a little y prime right there. So the derivative of y is 1, but it's y prime. Okay, and I'll give you some more examples. You'll see when the y's start getting more powers or more complicated, all you remember is you just do the derivative like you normally would for a y, but you stick on a little y prime right after it, multiply. That's that chain rule that I was talking about. So now I have 6x plus y prime equals 0, and our job is now solve for the y prime. So it means just get it by itself, and that's how we get this negative 6x. Now if you go back a slide, I know it's not going to show as well, but you see here that And they did make a mistake, just so you know. I forgot to point that out. That wasn't supposed to be a y squared. The derivative of this equation right here is just negative 6x. Little typo in the PowerPoint, sorry about that. But it's the same thing that we got here. We had the same equation, but because our equation was in a different form, we just go and we take every single derivative of every piece, and then you solve for the y prime. Okay, so I'm going to do more of these, like I said, and you're going to get an idea of how this looks. But let me get rid of this. Show you the next one here. Okay, so now what they're doing is they're taking the derivative of both sides, and this d dx with respect to x, and you do that to every single term. So like all four, like I was showing you earlier, and 6x, remember, anytime you take the derivative of something other than an x, you have this extra y prime right here. When you take the derivative of a y, it's a y prime. And that's how we end up getting that same answer there. Okay? So they come out to be the same thing. All they're showing is that they're identical here. Now I want to jump forward and show you what we're talking about here. Okay? Remember, the derivative is going to tell you the equation of the slope. Sorry, it's going to tell you the formula to get the slope of a tangent line at a certain point. So they're talking here about what happens when x equals 0. What are the tangent lines? Well, I'll show you the first one here. Okay, so the first one is going to be right there. There's a tangent line. When x is 0, you have this point right here, and there's your tangent line there. But if you notice, there's a couple of places we get x equals 0, because it's not a function. Here's another one right here, and you notice that one has a different tangent line. Look at the two. They clearly have different slopes. So our formula is going to be not quite the same as before here. If I keep going, there's actually more, because there's a 0 here. So if you look at all the tangent lines, there's that one earlier, there's that one, there's one right here, and there's also one right here. There's actually 4 different tangent lines, which are going to give you 4 different slopes. So how do we know what we're finding out? Well, we have to be able to go plug everything into some special formula that's going to have more than just an x. So here's our first case. We have a function right here where it's x squared plus y squared minus 25 equals 0. Now, I want to clarify, I don't like that notation right there. It's a little bit clunky, but this is the equation that we are talking about right here. And you may recall this is an equation of a circle, just a nice circle of radius 5 at the middle, but don't worry if you don't remember how to graph that. Not important. What you have to do now is we want to find the y prime. So treat it like it's 4 individual terms if you count the 0. When I take the derivative of each one, so that's going to be a 2x. This one's going to be a 2y. This one's going to be a 0. This one's going to be a 0. And then I purposely skipped doing a step here. What's going to happen is anytime you take the derivative of something that's not an x, like that y, we have to multiply by y prime. So that's the only difference in what we're doing. Other than that, everything is a normal derivative. All these derivatives are the same. So what we're left with is 2x plus 2y times y prime equals 0. And at this point, our job is get the y prime by itself. So all algebra here, if you look at all my terms, this one has a y prime, so I'm going to leave it over here. I'm going to move the 2x to the right, so it becomes a negative 2x. Then I divide both sides by the 2y, makes everything cancel, and I get y prime equals negative x over y, because of course the 2's cancel out. And that's our equation right there. Okay, so that's what's known as implicit differentiation, where you just take the equation where you're going to essentially get something more than just plain a y. You're going to get things like this, like a y squared, or a 7y to the third, whatever the case. You take the derivative like normal, but whenever you take the derivative of a y, you tack on that y prime, and then that's what we're trying to solve for. Okay? So when you see them going through the process, it's the same exact thing I just did right here. You don't necessarily need to do all this little extra stuff that they did here. Quite honestly, I want to make sure you know how to get down to this step right here, which is pretty much my first thing. The 2x is the derivative of x squared. the 2y, y prime is the derivative of y squared, and then it's all equal to 0. And then, of course, they solve it for y prime and get this. Okay? So there's your second example of what we'll be doing with implicit differentiation. Okay, now they're going to continue this on again like they've been doing here. Find the slope of the graph at x equals 3. Now notice they say the derivative at y prime at x3, you're going to get something, but watch what happens, okay? You plug in, oh, where are we going here? All right, let me go back up a step here. Let me show you where we're at right now before I give you the answer. So you see here, we have this equation right here. Y prime equals negative x over y. Now normally if I want to find the derivative, the value of the slope at a given x, I just plug in that x equals 3 and I would get a slope. But see, the problem is we got this y down here. It doesn't give me a number. It doesn't give me like 3/2 or 3/5 or 3 or something like that. I've got a mystery number. What happens is I have to go figure out what's the y value that corresponds with that one. I have to know what the y value is in order to plug it in here to get my actual slope. So our first step is we got to go back to the original equation right here. We plug in a 3 for x, and we need to figure out what the y is. Now, like I said, if you remember that this is a circle, we end up getting y squared equals 16, and we actually are going to get two answers, 4 and a negative 4. Okay, so let me cut out of here for 1 second and just kind of show you what is happening. Let me pull up some Desmos again. Just, you know, if you forgot how this equation looked, or this graph looked. So here's our graph up here. So we have the x squared plus the y squared minus the 25 equals 0. And you see it's this circle right here. Okay, now what they're asking is, what is the slope at x equals 3? Where here's x equals 3 right here. But notice there's a point here, and there's a point here, and they each have different slopes. So which slope are they looking for? Are they looking for this one, or are they looking for that one? That's where you have to determine it. Which one are we looking for? So this coordinate here is 3, 4. This coordinate down here is 3, negative 4. They're both good points, and you're going to see what happens when I go to this equation over here, this y prime equals negative x over y. Now you'll see what happens is I'm not just plugging in a 3 for x. I'm going to plug in an actual full coordinate, an x and a y, because my formula, my slope, my derivative, the slope of the tangent line right here, it has x's and y's in it. All the ones we've had to this point only had x's, but these have both. So at the coordinate 3, 4, when I plug that in there, I get negative 3 over 4. That's the slope. And if you look at the picture that I just drew or just graphed, you'll see that is in fact the slope right here, negative 3/4. That looks right. Okay? So now if I was to say, well, let's go look at it for that bottom point where it's still x equals 3, but now here's my derivative at 3, negative 4. So when I plug this in here, I get a negative 3 over negative 4. This one gives me a positive 3/4, and that's what this slope is down here. So you see how the formula for the derivative for the slope of the tangent lines, it still does accurately give you what the slopes are, but because there are multiple points where x equals 3, you're going to get different slopes, so you have to incorporate, well, which one do you want? What's the y value right there? And that's why we had to plug in a y, and we get our correct values. Okay, so that's the difference here, is you're going to get y's in the answers of the derivative when you're trying to find the slope. You're going to have to plug in x and a y because you have to be specific of at which point. It's no longer good enough to say at this x value. Okay, so in our problem here, they did the implicit differentiation. We got that already. Now we're getting the slope. And at x equals 3, you plug that back into the equation, you're going to get two different values. There's the 2 points I talked about, 3 negative 4 and 3 positive 4. When you plug them in, you get two different values for the y prime. Okay, and that's what's going to happen. So two different points in the graph, two different values of the derivative, and they actually graphed it here. I should have looked ahead a little bit. And there's where you get that tangent line has a slope of negative 3/4 because you plugged in the coordinate 3, 4 right here. That's 3, 4. You plug that in there, you get the slope of negative 3/4. Where if you pick the other one, you plug in the coordinate of 3, negative 4, you get this slope right here of that line. Okay, so that's what's happening in each of these cases. So now that we've got that established, that's the only new part. The hard part is we have to now apply this to all the old concepts. We have to use all those rules from before. So here's a great problem. All right, we have y minus xy squared plus x squared plus 1 equals 0. We want to find the y when x equals 1. Okay, so the question is find the equation of the tangent line at the point x equals 1. So they're just going to plug in 1 to start for x. And remember, you're plugging this into the original equation right here. That means you're going to get a y value. So when you plug x into the original, it spits out a y value. That's going to give you some coordinate, maybe 2, who knows. Okay, so what they've done is they've plugged in that 1 for x. Now they're going to solve for y. So rearrange and make sure you're clear what happens right here. You get y minus y squared plus 2 equals 0. They divided everything by negative 1 to make this a positive y squared. This becomes a negative y. This becomes a negative 2. And then we factor, and you get these two values right here. So we have two different coordinates that I'm going to put here. 1, negative 1, and 1, 2. That's from solving the original equation when x equals 1. We plugged in a 1 to that original, and it gave us coordinates. Notice I didn't have to graph this yet. I just wanted to get those coordinates because that's what we need for the tangent, the equations of the tangent lines. Now we have to figure out what the slope is of this. So in order to do the slope, we're going to take the derivative. Same old rule. All right? So I'm going to work this one out. I'm not going to look at what the slide has. We have y minus xy squared plus x squared plus 1 equals 0. Now the thing I'm going to tell you, leave yourself some room. Don't try to squeeze this in if you're writing this on paper. Give yourself some room to work because there could be multiple steps and multiple things you have to show here. Okay, let's get that right. Okay, here's our equation. Now, like I said, do the derivatives one term at a time. So for this one right here, the derivative is 1, but remember, because you're taking the derivative of a y, you put a little y prime right there. Okay? Now for the next part, remember, this is the product rule. So remember, it's one thing times another. Now, I'm going to incorporate that negative right there so that you see our two pieces. Okay, in fact, I'm going to use different colors for this just so you see exactly what's going on. I'm going to have a blue one, and I can leave the negative out front and just make sure you put the negative on everything, or I can stick it in there with that first piece, and that way I'm covered. So remember the rule. You take the first times the derivative of the second. Well, the derivative of y squared is 2y, and then again, I just took the derivative of a y. That's why there's a y prime here. Then you add, we're still doing the product rule here, and you take the second y squared times the derivative of the first, which is just negative 1. So what I want to point out here is, notice I did a y prime right here because we took the derivative of the y, so I had to put the y prime. Over here, I did not take the derivative of a y, I just copied the y. That's the product rule, remember? First times derivative of the second, and in this case, second times derivative of the first. This was not a derivative. This was the derivative right here. So because I did not take the derivative of the y, I don't have to put that y prime. And why I'm saying that is I don't want you to just start putting y primes everywhere because you think it should go there. It's only when you take a derivative of a y. That very first step, we took a derivative of a y right here, so I got a y prime. Here I took a derivative of a y, so I put a y prime, but not here. Okay, did not happen in that second case, so that's why there's a couple of y primes. Now, notice that gives you the derivative of that entire term right there. Now I do the derivative of this one, which is a 2x, and the derivative of the one, which is a 0, and that's, of course, equal to 0. So I've done the entire implicit differentiation, which is just a derivative of every single piece. Sometimes it becomes a couple of extra terms because you had the product rule. But now I'm going to simplify everything that I have. So this is just cleaning up what we have. Okay, then at this point, remember what we did before. It's getting, obviously a little more complicated, but what was the rule before? We need to solve for the y prime. Well, if you count this out, this goes back to our good old days of algebra here. I count 1, 2, 3, 4, 5 terms, if you want to call it that. These are all terms. 5 terms. Why I'm pointing that out is when you want to solve for a y prime, all the terms that have y prime, you put on one side. All the terms that don't have y prime, you put over here. Notice I didn't say y, it's y prime. If it has a y prime, you leave it on the left. If it does not have a y prime, we ship it to the right. Now what happens is, I'm going to recopy that whole equation up here. Okay, now we're still trying to get y prime. What I'm going to do next is I'm going to factor on the y prime out of these terms here on the left side. And I do nothing on the right side. Then I divide everything, both sides, by what I just left over from the factor. And then I'll move down here to the bottom. That leaves me with a y prime equals y squared minus 2x all over 1 minus 2xy. That right there is our derivative using implicit differentiation. So we took this equation here at the top and we did one piece at a time, all these derivatives. In one case, we also had a product rule. Then once the dust cleared, I had all these terms here, the ones I underlined in pink there, and I want to put all my y prime terms on the left, all my non-y prime terms on the right. Then I factor out the y prime, which is what we did up here. Factor out the y prime, divide this away, and now I'm left with this nice, tidy equation. Okay? So, pause, look at that. I want to make sure you understand where I got everything from, and I'm going to erase a little bit of this. Okay, because I still have to have room to work. This is just the start. We have the derivative, but now we need to figure out how to get the equation of the tangent lines. So keep reminding you, the derivative is going to tell us the formula for how to get the slope of every tangent line. This is a case just like that circle we had a couple minutes ago where there may be multiple points at x equals 1. In fact, we saw there are 2 points. Remember that? That 1, -1? I still have it on the screen on the right there. There are 2 points, and it's pretty likely that each of those is going to have their own tangent line, different tangent lines, which means you're going to get different slopes. So that formula that I just found in the box on the bottom right, that is going to allow me to find each of them. So if I start with this first point, 1, 1, 1, -1, sorry, I'm going to take this derivative that I just found. And I'm going to plug in all of these x's and y's to that And you see I get a negative 1 squared minus 2 times 1 all over 1 minus 2 times x times y. So that's a 1 times a negative 1. And now we are close to getting our y prime. I have a 1 minus 2 over a 1 plus 2. Looks like I get y prime equals negative 1 over 3. That is the slope that goes with this point right here. Okay? So now we have that. We have our point. We have a slope. And it goes back to the same exercise you've done for a couple of sections now. Now that we know how to find the slope of a tangent line, if they ask you to find the equation of a tangent line, get the slope, get a point, which we have both of, and now we're going to take those two and plug them into our good old favorite point slope formula here. Y minus y1 equals m times x minus x1. Y plus 1 equals negative 1/3 x minus 1. And that's pretty much your equation there. You can solve it for y if you want to get it equal into that nice y equals mx plus b. Either way, you're going to get that. But just to do that, we get, what is it, a negative 1/3 x. We get a plus 1/3 and a minus 1, so it looks like it's going to be minus 2/3. Both equations should be good there. Okay? So that's how you take and get the equation of the tangent line. Both of these are the same. They're the equation of the tangent line right at that 1 comma negative 1 point. Now we got to repeat the whole process at 1 comma 2. Okay, so I'm going to let you try that one. I'll show you here on the PowerPoint, but that's the process of doing. We do the same thing. We would have to plug everything in to this, get a new slope for this one, and then go plug everything into the point slope form again and get a second equation for a different tangent line. Okay, so pause that if you need to look at it some more, then resume. Okay, so if you watch how they work this out here, it's pretty much going to be a repeat of what we just did, pretty much. So implicit differentiation, and notice we have to go through, we're going to do derivative of each term, which we did. This is our product rule right here. Should look the same. And then they move over, and they skip that step in between that I have, where we move the non-x's over. Okay, and then we divide. I believe that's what we had. Did we get this right? Did they get it right? Yeah, I think that's what I had there. I wish I had written that down. Sorry about that. But now we plug in the 1. We get that negative 1/3. That looks familiar. And then they use the point slope formula and get the answer. That looks like the one we had. And then now we do the same thing at the other point, the 1 comma 2. So you go back to the derivative that we found right here, plug in the 2 for y's, here, plug in the 1 for the x's here and here, and then this tangent line has a slope of negative 2/3, and once again we go and we plug this into the point slope formula, and now the other tangent line is y equals negative 2/3 x plus 8/3. Okay, so I'll let you pause that as well if you need to look at that. And we'll move on. Now, same kind of thing here. Don't let this problem mess you up. The difference I'm going to tell you here is that we want to, and look what's going on here. They want you to find x prime for this equation x of t, and it's got all this. So let me just kind of talk about what's going on here. Let's write this out. Okay, now the part that is not exactly clear, and I want to try to clear it up for you, is when they want you to find x prime, and it's really not a common thing we're going to be doing, but they're kind of changing things up. Let me show you a second ago what we had. Remember, we were trying to find y prime, and when we were finding y prime, it basically is the same as go find d dx. Find the derivative with respect to x. Well, in this case, when they say find x prime, they're saying go find d dt. So t is our main variable that we're working with. Everything is with respect to t. So, kind of like earlier, whenever we didn't have an x, we had to go use that y prime. Here, it's the opposite. Anything that's not a t, when we take a derivative of something not t, like the x here, we have to tack on the x prime. So, show you how this works. Number one, we're going to find this derivative. And remember, this is going to be the product rule again. So we take the first times the derivative of the second. Remember, the derivative of natural log x is 1 over x. But because that's not our magic letter of t right here, I use the chain rule, which gives me an x prime right after it. So whenever you take the derivative of an x, when it's with respect to some other letter, like a t here, then you add on the x prime just like we were doing with the y prime. Then the product rule says, all right, we got to do the natural log of x times the derivative of t. Well, that's just a plain 1. Okay, and we're doing the same product rule over here. We take x times the derivative of the second. Notice I did not take the derivative of x. That's why there's no x prime here. But the second half of this is, well, take the et times the derivative of the first, which is 1. That is a derivative of x, so I put the little x prime there. And of course, at the end, there's a -1 derivative. That's going to be a 0. So as I clean things up, I get a t over x, x prime. I get a natural log of x. Over here, I get an x et plus et x prime. I guess we could say that. Either way. Okay, now there's a couple things to do here. And I'll show you what the book is going to do in a second, or what this slide will do, but I'm going to do it one way, and then we'll see what the other way is going to be. An option, and like I said, this is completely optional. I can multiply everybody by x just to make this cancel. Okay? Now, before I do that, let me go back one step and just kind of remind you all. In that very first term, see how we have a t and we have a natural log of, a t over x, that right there, times x prime. These things do not cancel out, this x and x prime. They're completely different letters. So don't think, oh, I got an x prime and x, I'm going to make everything cancel. If you have an x over an x, they can cancel. If you have an x prime over an x prime, they can cancel, but not when they're different letters. They're as different as a and b, or x and y. Okay, so now what I was getting at earlier was I can multiply everybody by x, and that's literally just to make this first little fraction here go away. So we have tx prime plus x natural log x equals x squared et plus x et x prime. Now notice, like this x et x prime, they're just three things multiplying together. The order doesn't matter so much. What matters is what we do in our next step, where we get all of our pieces that have an x prime, and we're going to get them on one side of the equation. And everything that does not have an x prime, we're going to ship it out to the other side. So we split up our equation so that the x prime terms are on one side and the non-x prime terms are on the opposite side. And the whole reason we do this is I want to factor out an x prime. So I'm left with t minus x et. And that's still equal to, I'm going to slowly erase things as I move down here. And that's going to be equal to this x squared et minus x natural log of x. We divide both sides by this. And what we're trying to do here is we want to just clean this up a little bit and get that x prime all by itself on one side. Okay, just got to get rid of some of this. So now this cancels. We have x prime equals this big fraction of x squared et minus x natural log x all over t minus x e to the t. Okay, so that is my derivative here. It's not going to be pretty. The more complicated our equations get, the uglier, the uglier our derivatives are going to be. But that is it. We have the x prime by itself. And now our last part is we need to plug it in right here at 0, 1. And make it clear, when they say 0, 1, that's the t, that's the x. I know that goes against what we're used to. X is always first, but this is kind of a backwards equation. So everywhere I see an x, I'm putting a 1, e to the 0 minus 1 natural log of 1 all over 0 minus 1 e to the 0. Now, it's not so bad. We get natural logs, we get all this stuff here, but at least with zeros and ones, a lot of things are just going to cancel off and go away nicely. So it's not going to be too bad here. So what I'm left with is x prime equals, remember, e to the 0 is a 1, so that's 1 times 1 is a 1. Natural log of 1, if you remember that, that's a 0, so that goes away. And on the bottom we have 0 minus 1, so it's a minus 1. Ultimately, x prime equals negative 1. Okay? So that's what we have there. That's the idea behind all of this. I'm going to get rid of that PowerPoint so you can see that. You don't need to have all that there, but that's what we have, and I'll let you pause it, and then I'll get rid of it and put the PowerPoint back just so you can see the steps here. So this is, let me bring this right back. So kind of the nicer look on each one. They're going to do each of them. You do the product rule. So that's what we had. And then cleaning up a little bit. Oh, they did the same thing I was saying. That's right. Okay, so we multiplied everything by x to get rid of that fraction. It just makes it a little bit easier to work with when you have your terms. Then you put the prime, x prime term to the left. You factor out the x prime. I had the x prime in the front of the parenthesis, and it does not matter because you're going to divide it away on the next step. And this is what we get, what we had. Then you plug in the 0 and the 1 into that equation that we just found, and all these pieces, and that's where we get the negative 1 from. Okay? So now we're going to get to the homework and just jump right in here and make sure that we're all on the same page on this. Okay, so once again, we're in our math 176. Oh, there, I just went out, sorry. Okay, so let's get to our assignments again. Leaving off with that homework number 8. We already did a lot of the first one. So now we're going to try to pick up these last 4. And you'll see they're all going to be about the same amount of work when you're doing them. Okay, so use implicit differentiation to find y prime, then evaluate it at the point 35. Okay, so how I would approach this. Number 1, when I see my equation like this, I just treat this derivative as 1 at a time. If I'm taking the derivative of a y, it's a 1, but it's 1 times y prime because it's a y. When I do the derivative of x, that's the same old song and dance as we always do, so nothing changes there. And now I just need to solve for the y prime, and that becomes a positive 6x. So there's my y prime. And this homework is valuable because it's going to give you that option to kind of check your work as you're going along, just to make sure you're getting it before you start plugging everything in. So there's our 6x. Not able to submit for some reason. Okay, oh, I got to do them both. That's right. Okay, so now this little notation right here. So you see that what that line and that little point means? It just means evaluate your derivative at the point 3, 5. Now, we had problems where we had to plug in the 3 and the 5. Before today, we were only plugging in the x, the 3. If your derivative only has an x, well then that's all I can plug in. I can just replace that with 3 and get an 18. If it has a y in it, then of course you're going to plug in the y value as well. But here what they're saying is the 5 didn't matter. Just plug in the 3 because this is a nice function. Okay? So that's what it is for number 39. Let's look at number 43 is our next one. And you'll see, same kind of thing. They're going to give us an equation. And this time we have to apply all of our rules. Remember, like I said last lecture, all of these rules are going to start stacking up one after another. So it's going to be, remember your product rule, remember your power rule, remember your quotient rule, the natural log rule, everything. They still are applicable here. So we have 3xy plus y plus 56 equals 0. So right here, remember, this is the product rule. Now, we haven't talked about this a whole lot, but where do we put the 3? It's 3 things multiplied, but it's only the variables that really matter. So I'm going to do it like this. The whole front is my 3x, and the whole second term is the y. So remember the rule for product rule. You take the first times the derivative of the second. Well, the derivative of y is 1 y prime. Then you take the second times the derivative of the first. Well, the derivative of 3x is just 3. Again, I'm not taking a derivative of that in that second piece. There was no derivative of the y. We kept the y as it is. That's why you didn't see me put a y prime. It's only when you're physically taking the derivative of a y that you put the y prime. Like this one right here. And then everything else is a 0. So if you count up your terms, everything that has a y prime, I want to put on one side. Everything that does not have a y prime, I want to move over. Okay, now you can spend this next step cleaning them up, but what I'm going to do is I'm just going to skip and go. Let's put these together, and let's move that 3y and make it to the right, make it a minus 3y. And then remember what we did last time. We factored, and then we divide both sides by that 3x plus 1. So we get a negative 3y over 3x plus 1. And that is the derivative, which is what most implicit differentiation problems look like. They have an x and a y in it. So that's what I'm going to plug in right here. We have the negative 3y over 3x plus 1. And notice the negative is in front. It could be in front. It could be up here with this, as long as you don't put it on both. Okay? Doesn't matter as long as you have it somewhere there. Now we're going to plug in the point negative 5, 4 into that said derivative that we just found. Okay, so everywhere you see a y, you're putting in a 4. Everywhere you see an x, you're putting in the negative 5, and you just simplify this. I get a negative 12 all over, and looks like a negative 14. And then, of course, simplify. It does say right here to simplify your answer. So I get a negative 12. Let me make sure I plug that in right. Yeah, negative 12 minus 14. The negatives cancel, and that looks like it's going to be a 6 over 7 positive. That's what my slope is at that one given point. Okay, so again, pause that if you need to see it. I'll clear it out. We'll go to number 47. And you see all these problems are very similar. We're doing the same kind of steps. Okay, now they want us to find the equations of the tangent lines. Okay, this one's going to be a lot more here. So what I'm going to do is I'm going to clear my screen a little bit, but I want to just copy the equation and then get rid of all this stuff just so we can have the entire screen to work. So remember, we have xy minus 13x plus 32 equals 0. And they want this to be when x equals 4. Okay, so now we have a little more work. First step, they want, and remember, they want the equations of the tangent lines. That's our goal here. So first step, it doesn't matter which one you do first. We need, in order to get an equation, we need a point and we need a slope. Okay? So let's just go ahead and plug in the 4 right here and see what we get. This is again going to give us the coordinates here. So we get 4y minus 13 times 4 plus 32 equals 0. 4y minus 52 plus 32 equals 0. 4y minus 20 is 4y equals 20. And it looks like y equals 5. So it appears we only have 1 point, 4, 5. All right? Check that over. Make sure you're seeing where I got this from. I replaced every x with a 4, and then I'm solving for that. And then that's solving for the y, and that's how I get the 4, 5. So now it's derivative time. In order to find this derivative of this equation, 13x equals 0, I have to do the product rule of that first one, that xy. So remember, it's x times the derivative of y, well, that's y prime, plus y times derivative of x, which is just 1. The derivative of negative 13x is negative 13, and then everything's a bunch of zeros. So now I want to get the y prime term on one side, the number on the other, and then I just, if there's more than one, we have to factor it out, but there's only one term that has a y prime, so I just divide by x, and I get 13 minus y over x. And remember, this is the formula to get the slope of the tangent line. So y prime equals 13 minus y all over x. Plug in those points, and that's going to tell you our slope. 13 minus 5 all over 4. 8 over 4 looks like we get a 2. So what I do know is that's going to be a 2 right there. And then last, we use these 2 bits of information to plug into the slope, the point slope formula. Y minus y1 equals m times x minus x1. Y minus 5 equals 2 times x minus 4. Y equals 2x minus 8 plus 5, so it looks like we get y equals 2x minus 3. There's the equation of the tangent line. Okay, now what I'm going to do here is, before I plug that in, this is obviously not something I'm going to say to do every time, but I just want to show you what it is, and it's going to be our way to check it before they tell us if we're right or wrong. I'm going to plug in this equation just to show you how the graph looks on Desmos. Okay. So it looks kind of like this. Not kind of. This is the graph right here. Okay. We're wondering what the slope is, the equation of the tangent line here at 4, 5. So if I zoom in a little bit, you see that coordinate 4, 5 right there. Okay. So what I'm going to do is just put that dot there. So you see that dot. Now, the equation that we found, y equals 2x minus 3, see where it is? See how it's tangent to this? It's hitting right there at that point. Just kind of confirming that that is in fact the tangent line. That's what we just found the equation of, this green line right here. Okay, so just by plugging into here, that looks good to me. Now we'll plug it into the right here on my MATLAB and see if this is actually the equation. Y equals 2x minus 3, and looks good. Okay, now sometimes they're going to ask for the derivative. Sometimes they're going to say, what's the slope of the tangent line at that point? Sometimes, like here, they want the equation. So you have to know what they're asking for so you know what to shoot for. Just kind of work backwards here. If they say, give me the equation of a tangent line, you hear tangent line, you think derivative. And then plug in the values to get the slope. And once you plug in those and you get the slope, like we got the m equals 2, use that along with the coordinate, which came from the original equation that I have up in orange there. That's going to tell you what we plug in for the point slope formula right here on the right to give you the equation. So it is obviously it's a multi-step process. You just have to take your time and do every little bit correctly. Okay, so let's look at this last one, number 51. Okay, just to show you what we have here on this. Okay, so we got two of them. We'll do number 55 also. I didn't see that one. So like the last time, I'm going to try to give myself as much room as possible. So I'm going to write the equation up here. We have 9 natural log of xy equals y squared minus 1. And they want us to find at the point 1, 1. And they want you to find y prime. And they want you to find slope of the tangent line to the graph. And it looks like that's it. Okay, so they don't want the actual equation this time. So these are the things that we have to find. So let's get to work. So they already gave us the full point right here. We need to go find the derivative. So remember how we do this. The rule is when you have a natural log, you take whatever's in the natural log and that becomes the bottom. So natural log of 1 over y, natural log of xy, the derivative is 1 over xy, but what we learned yesterday and today is we have to multiply by the derivative of this. So the derivative of xy is x times y prime plus y times 1. That's the chain rule right there. Okay, so look at that carefully and make sure you see where I got that from. That's the chain rule. And then it's combining it with the implicit differentiation that we learned today, where when I take the derivative of a y, I have to do it normally, but then I got to put that y prime there. Then on the other side of the equation, it's a y squared. That derivative is 2y, what we learned today, times y prime. And of course, the derivative of negative 1 is a 0. So I got a lot going on here. What I'm going to do is what we did earlier on the other problems. Let's multiply everything by xy to get rid of this fraction. Okay, so what that's going to turn out to give you is, well, that'll make this cancel. And all I have left is a 9xy prime plus a 9y. That's the left side of my equation. So make sure you see where that's going. I distributed the 9, and then, of course, the xy canceled. Over here, remember, I don't even need that 0 there. That's gone. But I'm multiplying this all by xy, so this is going to be a 2x y squared y prime. The reason I'm doing all this is to break it down so I just have nice, simple terms. Now, they're multiplied, lots of pieces to them, but I have individual terms, so I need to look at that and say, okay, which of these terms has a y prime, which of them does not, and that's how I know who to move where. So this has a y prime, I leave it here. The other one is a y prime on the far right, so I'm going to move it over. And then, of course, this 9y didn't have it, so I'm moving it to the right. Y prime's on the left, non-y prime's on the right. Factor out. And then divide both sides by whatever that parenthesis was. So we have a negative 9y all over 9x minus 2x y squared. Now, some people are going to say, well, can you cancel off those 9s? You can't unless it cancels from every term. Because there is no 9 over here, there's no canceling. So even though you see one right above the other, resist that temptation to do this. Oh, I erased it. Sorry. What I was trying to say was, don't do this right here. They do not cancel. You have to leave those as is. Again, it's because that second term on the bottom. But we have our derivative here, okay? And the questions, what they ask for? Yeah, they wanted to get y prime, so we have that. Let's see if they'll let me plug it in. Yeah, I got to plug them all in at once. So let's just go and get the other part here. Then they want you to find the slope, which means, okay, take this derivative that we just found, and we're going to replace every x and y with 1, because remember, it was this point up here, this 1, 1. So that goes right here. 9 times 1 minus 2 times 1 squared. Y prime equals y prime equals negative 9 over 9 minus 2. Y prime equals negative 9 over 7. That appears to be our slope. So, trying to check over real quick, make sure I didn't do anything wrong on that one. But we'll find out in a second. If we get it wrong, we'll troubleshoot and see what we can find. Okay, so there's my derivative. Now we evaluated it and we said we got negative 9 over 7 as the actual slope. And we have it correct. So again, let me get rid of this, let you pause it, make sure you see where I got all this from. We answered the questions that were there, and we'll go on to number 55. So you see there's definitely not as many questions. You know, we only had to do 4 or 5 today in the ones that I'm doing for you, but they do take more steps, take a lot more time to do, so we have to do something else. So we have the speed of sound in air is given by the formula v equals k square root of capital T, where v is the velocity of sound, t is the temperature of the air, and k is a constant. It is known that the derivative of t with respect to v is 2 square root of t all over k. So they want us to find dv dt. So kind of look at these two. This and this, notice they are different, okay? So to be clear, what happens is when I see dt dv, it means this bottom one, remember, this means with respect to v. So it means if you have a t equation somewhere and there's a bunch of v's in it, take the derivative. That's what that's saying. When there's a dt, it means that equation we're taking the derivative if you can get a t equals to something. Well, on the other hand, what they want us to find is they want us to find dv with respect to capital T right here. Okay? Now, the good news is, or sorry, just so I'm repeating what I just said, it means if you have an equation that's v equals something with a bunch of t's in it, take that derivative. Well, we have that right here. That's the derivative that we need to find. We have the v equals k square root of t. We want to find that derivative with respect to t. Okay, so that's our first question. And then they want us to discuss the connection between the two. All right, so I'm trying to see what that third part's going to be here. So d. All right, so they want us to set up the implicit differentiation. Now, what happens here, plug this in, basically, this is just going by our formula. If v equals k squared of capital T, when they want you to find this, they want you to find k square root of t. This is, like I said, it's just the setup, getting this problem ready. Now we're going to actually find the derivative. So I'm going to move this down. I'm going to clear out most of this other stuff that I've drawn. And we're going to find the derivative of that equation at the top. Now remember, dv dt, it means find the derivative of the v equation, which we have there, with respect to capital T, because that's what was on the bottom. dv dt. So it means when you have t's, you don't have to do any kind of chain rule. You don't have to write that t prime or anything like that. Those are your letters. Now the other important part they said was k is a constant. Okay, it's not a variable. If it was a variable, we'd have to do product rule. We'd have to do a k prime. But because it's a constant, you treat that like that's a 3 or a 9 or whatever the case. It doesn't have any bearing on this problem. So I'm going to rewrite it as t to the 1/2. And now I'm going to find that derivative. The derivative of this, once more, dv dt is going to be the 1/2. We're just applying our good old power rule, where we move the 1/2 out in front, we take the power and we subtract it by 1, and this is, believe it or not, the derivative. 1 over 2, we have a k on top, and remember that t becomes a 1/2 on the bottom. So I'm just cleaning it up right now. That's a k over 2 square root of t. That's our derivative right there. That's what we're going to plug in. Not that. That's what we're going to plug into this second question right here. So we have a k over 2 square root of t. Eventually I'll get there and check that. We have that one correct. And now I want you to compare the two. So remember, here's dv dt. We found that. Earlier, they told us dt dv is 2 square root of t over k. So if you look at these two answers, what's the relationship? Okay, are the inverses? They're definitely not equal. Are they opposites? Are they reciprocals? Now, we know they're not equal, so I'm going to get rid of the b. They're not opposites because opposites means it's the same thing but one's negative. This is the part where people make the mistake on. What's the difference between reciprocals and inverses? Well, inverses is a whole different function. All right, that's the one where you replace x's and y's, or in this case, you replace the k's and the t's. So just to show you for fun, the inverse of this, in this box right here, the inverse of this thing, the inverse, is when you swap the positions of the t and the k. So where this was a k, we put a t. Where there was a t, you put a k. That's what it means to be the inverses. That's not what we have over here. All right, so what we have is, pure and simple, these two things I have boxed up, these are simply reciprocals of each other, and that's the answer. That's the question at hand. So for the last part, we're looking for reciprocals, and that's it. Okay, this problem sounds a lot more complicated, but that's all they wanted right there. That's really all they're asking. Okay, so at this point, that is everything that you need to finish this homework for week number 8. We have all these problems done. You should be able to do them all. Again, they are going to take some time, some of these. Some of them are real quick. Some of them are going to take more time. So my recommendation is do not try to wait until Monday next week or Sunday night or one day to do all this homework. You literally should take 3, 4, 5 days if you can and do 5, split these problems up. There's 55 problems. Ideally, in my perfect world, if you can do 11 problems a day for 5 days, you have it. But at least try to split it up a couple days, a few days, because this gets tiring. It gets, you kind of start losing track of where you're going here. But if you mix it up a little bit over the days, it'll really stick with you. Okay, so like always, ask me some questions. You're good to go on Chapter 8. Don't forget about what your assignments are. Keep track of this one and look for Week 9 videos coming up in a few days. All right, have a good one.